Okay, so I just need to know. Oh, yeah, Adam, I can do that. Question was, can I open up the previous test? And so you can see what you got wrong. And the answer is yes, I will do that. Let me make a note of that. I won't do it right now, but I will do it. So what questions do you have on progress check A, if you have any, on unit 5?
4.
Mr. Alquist,
Mm-hmm.
I'm a bit behind. I haven't done it yet. Can I go do it right now?
Yeah, but you might miss explanations, but whatever you
You're
want.
recording it. I see.
I am recording it, Jonah.
Yep.
Okay.
Right. Have a good one.
Yeah,
Have a good
you
weekend.
too.
Bye.
Bye. All right, let me look at, let me open this up. So I got 4, 6, 7, 8, 10. Those are the ones that are listed right now. I can do more, but that's the ones I will start with. I gotta open up my, yeah, if you didn't do it and you're like, well, I don't really want to watch the explanation because I want to do the assignment first, and you want to go do it now, I will post this video on, well, it'll be on, I wonder where I should put it. I'll probably put a link on the Schoology folder for when I assigned this. So I'll do something like that. Okay. So let me get this all set up. All right. All right, let me open the chat up in case you have questions that I don't go over. So let's look at number 4. Let me just make sure. Okay, so so the question is, let f be this function given on this closed intervals of the following intervals on which the mean value theorem can be applied. So the question is, when can the mean value theorem be applied? Well, and so you have to go back to your mean value theorem notes, really. The key on your mean value theorem notes, if you go back and look at them, what you'll see is for the mean value theorem, it says if f is continuous on AB and differentiable on AB. So continuous on the closed interval, differentiable on the open interval. Okay. Which of the following can be applied? And so one of the things that you have to worry about on this particular problem is we have an issue when x is equal to 4 and when x is equal to -2. Because on those values, our function is not continuous. So if we include one of those, we can't really apply the mean value theorem because suddenly the mean value theorem is not, this function is not continuous at 4 and -2. So it's not going to be differentiable either, right? So if you look at that, we're okay with this first one from 1 to 3, -1 to 3, because that doesn't include 4 and it's continuous and it's differentiable on there. 5 to 7 we're okay with as well because that excludes these two problem places. But if you look at this one, 1 to 5, the issue is we have a problem with the value 4. So that's why when you look at this, which of the following can be applied? It's only 1 and 2, and the big issue becomes 3 is not included because we can't use the mean value theorem on interval Roman numeral number 3 because from 1 to 5 includes one of those issues. Any questions on that? So remember, on the mean value theorem, there's a pretty strict, this is what you can use now. If you have this condition, you can use the mean value theorem. If you don't have this condition, you can't use the mean value theorem. So you got to look at the condition that's given to you. So let's look at 6. So looking at 6, kind of the same thing, only with 6, when you look back at your notes for the extreme value theorem, it talks about f is continuous. Might say it's f is differentiable. Maybe it's differentiable, if I remember right. I think it's continuous, if I remember now. So f needs to be continuous on some interval a to b, but it has to include a and b. So it has to be continuous on the closed interval. And take a look at this problem. We have issues when x is equal to 1 and when x is equal to -3. We have issues there. Well, look at what happens because we have discontinuity. At these x values. Notice that on every other answer other than C, it includes those. So we can't really use that. We can't really use the extreme value theorem if this is the if part, and then you'll get a then part. But if we have this condition that we have to meet and we don't meet it the same way we didn't meet it for the last problem, that condition is pretty strict. If you can't meet that condition, you can't use that theorem. Does that make sense? Is everybody okay with that? I'll take your silence as a yes. If you have questions, stop me. So that's 6. Let me look at 7. So again, the function f has no absolute minimum and no absolute maximum on its domain. Why does this contradict why does this not contradict the extreme value theorem? So what do you notice right away? Somebody unmute themselves and tell me, what do you notice about the first sentence on this? Or type it in the chat.
It's not closed.
Exactly, it's not closed. It's not a closed interval. So if it's not a closed interval, we have a problem. Again, this right here has to be met. We have to have that stuff that I'm highlighting. If I don't have that stuff that I'm highlighting, we cannot use it. And notice that this is an open interval right here. So so that's why it doesn't contradict it, because you can't even really use the extreme value theorem if f is not a closed bounded interval. Okay. Any questions on that? So like all 3 of these first questions that I just answered really have to do with that if part being super, super important. Okay. Let's look at this one. Okay. One of the things with this is, notice right here, what do you notice, right? I'm gonna try to highlight it, shoot. I'm gonna try to highlight it, my mouse is just slow. What do you notice in that that would make you question something? What's not given in that statement? Somebody other than JC, tell me. So Nick put it in he direct messaged it to me, but he's absolutely right. Differentiability, right? So for the mean value theorem, we needed continuity and differentiability. For the extreme value theorem, we needed continuity. If you remember from first semester, for the intermediate value theorem, it said if f is continuous on a b. So for the intermediate value theorem, we just needed continuity. So the extreme value theorem, you needed continuity. The intermediate value theorem, you needed continuity. The mean value theorem, you needed both continuity and differentiability. And so which of the following statements could be false? It's B, because B, you need differentiability. In order to use B, you need both continuity and differentiability. So when you look at that one's coming, we can't really guarantee that because we haven't met that criteria. So we haven't met that criteria, so suddenly we can't use that mean value theorem formula because it doesn't say anything about differentiability on here. So if you don't have it, you can't use it for that one. Any questions on that? Okay. Let me look at 9. So 9 looks like this. Let f be the function defined by this. Which of the following statements is true? You start to read this and you kind of go, well, shoot, if I have to read this, and it's talking about f decreasing, f increasing, f decreasing, f increasing, and this is f, you should kind of think to yourself, oh boy, if I'm going to start to answer questions about f increasing or decreasing, if f is increasing, f prime needs to be positive, and if f is decreasing, f prime needs to be negative. Now, if you look at that, maybe that means you can throw out C for an answer right out of the gate, right? Now, I know that you know D is the answer because I put it up there. But here's how you would do this: is you'd say, okay, I really need this information is how I'm going to make my conclusion. So if f of x is equal to x cubed minus 6x squared plus 9x plus 4, then f prime of x is going to equal 3x squared minus 12x plus 9. And so now what I need to really kind of do is kind of say, okay, if I take this thing and I figure out when it equals 0, I'm going to start to get some information about when this function f is increasing or decreasing based on the sign of the derivative. So if I factor out a 3, I'll get x squared minus 4x plus 3. So doing that factoring, x minus 3, x minus 1. So our critical numbers are when x is equal to 3 or x is equal to 1. So now I just have to test those, right? I got to go through and I got to say, okay, I got a critical number here at 1. I got a critical number here at 3. If I'm going to start testing values, I'm going to test maybe 0 here, Now, you might say, well, we can't test 0. Well, I can still test 0 on this interval because it's still defined there. I'm probably going to test 2 here because that's right in between. And I'm going to test 4 here. Now, I don't have to test out here because it's really not, I don't have to worry about this part out here because it's not something that's part of my answer. So what I really got to test is some of the values in here. So if I test 0 in, and again, I'm going to test it on the derivative. I can test it on this derivative. I can test it on this derivative. I actually think the factor derivative is probably the easiest one to test, whether something is positive or negative. Sometimes I think that's easier than doing some multiplication, because what I can see is I can see that f prime, if I plug in 0, I have a positive value here. And if I plug in 2, I have a negative value here. What that means is f is increasing here and f is decreasing here. So now I just try to read what the heck's happening. And this is the D is the only one that matches up with my sign chart. Any questions on that? Okay, last question that was asked was this one right here. Again, here's a question of on what open intervals is f decreasing? Okay, so again, we're kind of going up here and we're going to use this. Specifically, we're trying to figure this out to figure when f is decreasing. So we're going to need a derivative. We're going to then need to do some factoring. And we're also going to need to look back at what the natural log looks like. And so we're going to kind of review that, which actually will help you. This portion will help you with the FRQ that you'll have next Wednesday. Okay. So this portion will help you with the FRQ that you have next Wednesday. So you got this function f. It's defined by x times the natural log of x. X is greater than 0, so that's an important piece. The reason that's in there is that's a restriction of the natural log function anyway. We're trying to figure out when f is decreasing. That's going to happen when f prime is negative. So we're going to need to find a derivative. Because this is times, we're going to need to use the product rule. So we're going to say f prime of x is equal to 1 times the natural log of x plus x times 1 over x. And the derivative of the natural log of x is 1 over x. Any questions on that? Okay. So what we have is we have the natural log of x plus 1 is equal to 0. Any question on that? Let me with there. Yes? Okay. So let me make sure. Did I do that right? So what I have is I need to know when the natural log of x is equal to -1. Now there's a couple of different ways I can do this, okay? If you remember from your pre-calculus or advanced algebra days, or remember what we did this actually way long ago, the beginning of the year, what we did is if we can do it a couple different ways. One way we can do it is we can know that the natural log of x equals y is the same thing as writing e to the y is equal to x. We could do that. Or we know that if we have the natural log of x equals y, and we raise both sides to the power of e, these go away, and you get that. Okay, so those are the notes that you maybe would have in your head. So from that, we know that x has to equal e to the negative 1. Any questions on that? Okay. So we got to figure out the open intervals on which f is decreasing. We know that we have this for a derivative. That right there is our derivative. Now here's something that I talked about a while ago, but I haven't talked about it for a little while. This graph is the graph y equals the natural log of x, and knowing that is a really important piece. And knowing that that point right there is the point 1, 0, because the natural log of 1 is equal to 0. Okay, well, that's an important piece. Okay, so that's an important piece, because what we have is we have a critical number that is 1 over e. We have that critical number, and e is around 2 something. Okay, so we know we can't go past 0 over here. Okay, we can't go past 0. We know we got a value right here, 1 over e. Sorry, hold on. And we know that 1 is somewhere up here. Okay, so 1 is somewhere up there. Okay, and so somewhere back here is 1 over e. Somewhere back there is 1 over e. Does that make sense? Is everybody okay with that? Okay. So that means if we test a value in this area, so it doesn't matter what it is, maybe x is equal to 1/4, that means that we're going to have a negative quantity. Let me think how the best way I can explain this. Let me maybe a better explanation is if I go out here, this is if I test I got this derivative f prime of x equals the natural log of x plus 1. So if I test like x equals 5 out here, that'd be somewhere maybe up here. Notice that that would be positive. Does that make sense? Why that would be positive? Are you there anymore? Okay, so that's positive. We are looking for when f is decreasing. Look at all of our solutions over there. Notice that the only one that would be at all a way to deal with it would be back in this area back here, because if we think about, we need this derivative to be negative. We can get it to be negative if we go down, if we go way down here, we can get that to be negative, because this is going towards negative infinity, right? So we can get that to be negative. That's why A is the only answer. That's a pretty tough question. One of the things that you're going to want to know for the FRQ is what this graph looks like. Okay, you got to know that graph. Any questions on that? That's a pretty tough question. Any other questions that I did not go over on this progress check? All right. Then if you didn't do this progress check, you should do it. If you did do this one, fabulous. Move on to progress check B. If you were in Johnson's class and you already did progress check B, then I would tell you to look it over the answers that you have. Make sure you still understand them. Make sure you understand the ones that Johnson just gave you, because that's the new material. But you should look that over again. Okay? Are you good? Okay.
Thank you, Mr. Alquist.
Thank you, Alquist.
You got it.
Thank you.